So this afternoon's talk is by Yifei He. It's again about cluster connectivities in the critical paths model. So these objects were introduced this morning by Jacopo Vitti. And now this afternoon we'll have another side of the story by Yifei and collaborators.
Okay, thank you. So first, I want to thank the organizers for putting together this nice program and also for giving me the chance to speak here. I'm going to talk about 4-point cluster connectivities in the 2D critical paths model. This is based on these two papers that we finished last year. The first one is a work together with Linnea Grant-Samuelson, Jasper Jacobson, and Yubak Salah, where we study some connections between the paths model and the minimal models on the lattice. And then there's a second paper together with Jasper Jacobson and Yubak Salah, where we look at more on the CFT side. So the plan for the talk is the following. I'm going to start with a brief introduction where I'm going to keep some minimal amount of information such that the talk is self-contained and also give some motivation of studying these objects. And then I'm going to move on to some relation between the paths model and the minimal models on the lattice. And the idea here is to understand by this comparison, understanding better the spectrum that appear in the paths connectivities. And the next part, we're going to bootstrap the paths 4-point connectivities. And here I'm going to introduce the concept of the interchiral conformal block. And I'm also going to analyze the bootstrap results. And the last part is a very short conclusion. Is it possible to erase these dots here? I think I could try to do this. Okay, that looks better. So, okay, so we start by considering the percolation model, which is simply stated on the lattice, where between two lattice sites, there is a certain probability of forming some random bonds. And then for a given configuration of these bonds, the connected parts of these bonds are called clusters. And when we try to use this percolation to model the real world physics, these bonds can represent very different physical properties. And for a certain critical value of this bond probability, the mean cluster size diverges, and there's a cluster percolating through the system. This is a signature example of a geometric type of phase transition. And it has been a long dream to understand the precise CFT description of such a phase transition. So in this kind of geometrical critical phenomenon, the really meaningful physical observables that one can talk about are correlation functions of the geometrical type. And one example is given by these cluster connectivities. If we consider the example of 2 points, then one can ask the question of the probability for these 2 points to belong to one cluster. And this can obviously be calculated by summing over all such configurations divided by the partition function, which in this case is just 1 for percolation. And I'm going to indicate this kind of cluster connectivities with pictures like this, where we have 2 points, and then they're connected by one cluster. And what we want to understand is how to compute such quantities in the field theory description, since it seems like a very non-trivial task, since this encodes a lot of non-local information. So a starting point to understand these critical geometrical critical phenomena is to map them to the usual spin system that we're familiar with. And this is provided by the paths model. In this case, at each lattice site, there is a spin variable which takes q different values. And then between the neighbors, there's a ferromagnetic interaction taking this form. So when Q goes equals to 2, we have the Ising model, and when Q equals to 3, we have this 3-state Potts model. And what this Kronecker delta function here means is that if we consider the two neighboring spins having the same value, then we say that between them, they form a bond. And then if they have different values, then there's no bond. And in this way, a given configuration of these spins can also be equivalently written in terms of a cluster configurations, which are the connected parts of such bonds. And all the spins that lies on the same cluster necessarily share the same value of spin, which assign a color to the clusters. And in terms of the partition function, originally we have a partition function where we sum over all the spin configurations, each one with a certain Boltzmann weight. And then in this rewriting, this means we can also rewrite the partition function in terms of a sum over all these cluster configurations, each one with a certain weight that takes a form like this, where we have some number to the power of the number of bonds, and then the parameter Q to the power of the number of clusters. So here Q tells us the weight of each cluster. So in this reformulation, originally we have the Q to indicate the number of spin states, which has to be an integer, but now the Q is just a parameter of the weight of the clusters. So the model is analytic continue to arbitrary real values of Q. And at the critical point, this parameter V here takes square root of Q. And for Q between 0 and 4, the model has a second order phase transition, which is described by a CFT. And then one can consider taking the limit of Q goes to 1, where there's only one possible colors for the clusters, and this reduced to the percolation situation. And for the correlation functions, we start by defining an order parameter, which is given in this form where alpha goes from 1 to Q. And then this definition is such that when we sum over alpha from 1 to Q, we get 0. And then one can calculate the correlation function of these order parameters in the usual sense that would compute its statistical average. And then from what we said before, this can also be written as an expansion over these cluster configurations with the operator insertion. And by playing with some combinatorics here, one finds that the correlation function of this order parameter is linearly related to the cluster connectivities that we're interested in. And this is the work by Delfino and Vitti in 2011. At the critical point, in the scaling limit, we expect that these quantities are written in terms of CFT, two-point functions of conformal operators in the CFT. And this operator, we're going to call it the spin operator. And you can think of it as the operator inserting a cluster into the system, let it propagate until it meets another spin operator, which takes the cluster out. So what we are going to focus on here is the 4-point cluster connectivities. The definition is very similar to before in the 2-point case. And there are 4 particular interesting 4-point cluster connectivities that we're going to study. Suppose I label the points as 1, 2, 3, 4 in this way. Then the first one is what we call PAAAA, which is the probability that all 4 points belong to one cluster. And then there's a second one where we have 0.14 belong to one cluster, which here is labeled by A, and 0.23 belongs to another cluster, which is labeled by B. And this is the PABBA. And similarly, we can define the other 2. There's a question. Yeah.
Hi, I have a question. So, sorry, let me turn on. Oh, I'm sure. Okay, something is. There's another set of exponents that is, operators maybe, and exponents that are known exactly from Coulomb gas. which are related to the behavior of the perimeter of the cluster, right? The multi-leg exponents. Are they in any way related to those that you're talking here? Is there any relation whatsoever or not?
I think it's gonna appear in the spectrum in these correlation functions. So as a 4-point function, when you can think of it as taking an OP of 2 spins, and then this probes the spectrum of the CFT, and I think the multiple legs operators are going to appear in the spectrum. So
so it's non-trivial. It seems to me non-trivial because the points that you're considering can be inside the cluster, right?
Yeah.
The perimeter is only sort of outside, so it's not clear to me how this.
You're talking about this like in the case of pods, there's this 4-leg operator, for example, which actually connect like 2 clusters.
Yeah.
Okay, so yeah, I think these exponents appear in the spectrum here, but maybe we can come back to this later. I mean,
sure.
Yeah.
Okay. Thank you.
So from the analogy before, we are going to we're going to think of this 4-point cluster connectivities as some 4-point functions of the spin operators in the CFT. And what we want to know is how to determine these quantities. So at this point, I want to say a few words about the POTS CFT. We have said before that for Q between 0 and 4, there's a second order phase transition. We can parameterize the Q in this way, where X takes continuous value from 1 to infinity, which covers this range of Q. Then the central charge of the CFT is taking the value, continuous value from -2 to 1. So in general, these POTS CFT are non-unitary. And in fact, recently it has also been understood that they are logarithmic. I'm going to briefly mention this in the end. On the other hand, for the operators that appear in the CFT, we can use the usual CAC parameterization.
I've just a quick question. So are you saying they're generically logarithmic, or they're logarithmic just for special values of X?
So the recent work is that people have understood that they are generically logarithmic, not just at the rational point.
I see. Okay, thank you.
So the spectrum can be parameterized using the CAC parameterization, which means that the scaling dimensions of the operators can be indicated with 2 indices R and S. But in this case, they can be fractional numbers. And in particular, the order parameter, which is the spin operator, takes the indices 1/2 and 0. So we see that the operators appearing in the POTS are in general non-degenerate, which means that these operators do not have a null descendant which decouples. And this further means that their correlation function, like the 4-point function of the spin operator, does not satisfy the BPC equation. So one cannot use this way to solve for these quantities. So some new ideas of how to determine these 4-point functions are the conformal bootstrap approach, which we can consider these 4-point functions of the spin operators and expanded using the conformal blocks, where we have some spectrum, and each operators in the spectrum comes with a certain amplitude. And when I talk about these amplitude, you can think of it as to mean the square of the OP coefficients of fusing 2 spin operators with some other operator which appear in the intermediate channel. But in this case, we're also going to have some geometrical labels which indicate which cluster connectivities that we're talking about. Then, given a spectrum, one can solve the crossing equation numerically to determine these amplitudes. And this way of understanding the cluster connectivities was first, this this the first attempt to bootstrap these cluster connectivities was done in this pioneer work by Pico, Hibou, and Santa Chiara. Although it turns out that the thing that the quantity they're bootstrapping is not quite POTS, which I'm going to come to in a few slides, but they have also provided some efficient numerical implementation of this approach. That's an approach that we're going to use, although I'm not going to talk about the details of the numerics. So what I'm going to do in the following is to first describe the spectrums that appear in the POTS connectivities, and then we'll bootstrap these amplitudes. So to understand the spectrum, we're going to go into another formulation, which is in terms of the loops. Suppose we start with some configuration of the clusters, then we can take the midpoint of each plaquette to form a different lattice, and then connecting these red dots to form loops in such a way that they bounce off the clusters. This way, each configuration of the clusters is equivalent to a configuration of the loops, which means that we can also write the partition function as expansion of diagrams of such loops. And at the critical point is given by such expression where we can read that each loop in a configuration carries a weight square root of Q. So in this language, the cluster connectivities can be also expressed as, for example, the 2 points belonging to one cluster. We can say that the 2 points are wrapped by some loops, and the 4 different 4-point cluster connectivities are can be drawn in terms of these loop diagrams. So why are we interested in these loops? Because if we're, in fact, understanding these loops will help us understand the spectrum that appear in the connectivities. And this is the work done by Jasper Jacobson and Yvette Salah in 2018. What they have done is to put the system on a cylinder, and then the loops that, the loop configurations on the cylinder can be described by an algebra, which is called the affine temporally leap algebra. It's generated by some basic elements of these type with their algebraic relations. And then what one can do is to extract the eigenvalues of the transfer matrix on the cylinder. And in the scaling limit, these eigenvalues give us the scaling dimensions of the spectrum that appear in the connectivities. On the other hand, these eigenvalues also comes in terms of irreducible modules of these affine temporally leap algebra. And to translate it into a more CFT language, each of this module includes an infinite tower of Virasoro primaries and their descendants. And combinations of such modules will enter the spectrum of these different connectivities. So we can actually plot the spectrum that they found for these connectivities, the scaling dimension as a function of Q from 0 to 4, and we'll see this very dense spectrum. So with this spectrum, it seems like we're halfway there to find these connectivities. So one can try to, for example, bootstrap to find these amplitudes. But before we do that, we're going to take a small detour to revisit some aspects of the minimal models. So why are we interested in the minimal models at this point? This is motivated by this first bootstrap attempt that I mentioned earlier. What they have done is to consider a 4-point function of an operator whose conformal dimension coincide with the conformal dimension of the pot spin. And then through the bootstrap, they find a very simple spectrum which appear in this 4-point function. And then on the other hand, by comparing with the Monte Carlo simulation, they find that this 4-point function, in fact, gives a very good description of a certain combination of the Potts connectivities. We can plot these, the scaling dimension of this very simple spectrum that they found on top of the Potts spectrum that I mentioned earlier. These are indicated by these green lines, which we can see that it covers a relatively sparse subset of the Potts spectrum. And later it was understood that this spectrum was in fact an analytic continuation of the type D minimum model spectrum to a generic value of central charge. And sometimes I'm also going to refer to this as a non-diagonal generalization of the C<1 Liouville theory. I hope that's not too confusing, but the point here is that this the amplitude appearing in this 4-point function in this Liouville case is analytically solved in this paper. So the first thing that we want to understand is why this analytic continuation of the minimum model spectrum would give a good description of the Potts connectivities and what we can learn from here about the Potts spectrum. So to do this, we revisited some old work from the 1980s. It was known back then that there is in fact a lattice realization of the minimum models, which is given by the ADE RSOS lattice model. In this model, each lattice site, instead of having a spin variable, is mapped to a node of thinking diagram of the ADE type with the restriction that neighboring sites on the lattice map to neighboring sites on the thinking diagram. And we won't have time to talk about details of these models, but the key point is that they also have a natural formulation in terms of clusters and loops. And this means that the partition function and the correlation functions can be expanded using such cluster and loop configurations. So the strategy that we took was to look at this 4-point function that comes from the minimal models on the RSOS lattice and to understand more precisely their cluster and loop expansion, and more importantly, how it's related to the Potts connectivities. So what we have found is that in the case of type D, which is the 4-point function that they're studying, this 4-point function is given by expansion in terms of loops precisely of these two types. The first one is the type AAA, where we have all 4 points wrapped within loops. And the second type is ABAB, where we have some loops that wraps around 2 of these points. But in this case, the precise interpretation of these loops are different from that of the connectivities. Suppose we consider the system on a 4-time punctured sphere. Then for the loops that are contractible on the sphere, they have weight square root of Q. And for the loops that are not contractible on the sphere, for example, these loops here, then their weight takes the sum over the eigenvalues of the adjacency matrix of the thinking diagram, which is much more non-trivial. And this is to be compared with the case of Potts connectivities, where all loops, contractible or not contractible, have weight square root of Q. So the 4-point function that they studied was, in fact, should be interpreted as the following. The first term is precisely the Potts connectivity AAA, since in this case, we have all the loops are of this type, which can be contracted on the sphere. So there's no difference between this quantity and the Potts connectivity. But for the second term, there are some non-contractible loops where the interpretation is different from the Potts connectivities. And we're calling these quantities pseudo probabilities, since on the lattice, they're no longer some probability quantities. And the difference between these quantities with the Potts connectivities involves some unlikely configurations, which would be challenging for Monte Carlo to detect, which explains this good approximation. So now with this, what one can do is to, and since these pseudo probabilities are also correlation functions of a geometrical type, one can put them on a cylinder and again, use the technique that was used for the Potts connectivities to look at the eigenvalues of the transfer matrix and extract the spectrum appearing in that. And what we find is that the spectrum involved in these quantities are almost the same as the Potts connectivity spectrum, which includes a lot of states. And in general, they comes in terms of irreducible modules of the affine temporally representation, the algebra, sorry. So there's also something amazing about how these eigenvalues contribute to these geometrical correlation functions. Suppose we take some eigenvalue which appears in the spectrum of two different Potts connectivities, let's say AAA and ABAB, then the ratio of their amplitude depends only on the parameter Q and which affine temporally module it belongs to. And on the other hand, suppose there's some eigenvalue which appears both in the Potts connectivity and the corresponding pseudo probability, then again, the ratio of their amplitudes depends only on the parameter Q and its affine temporally module.
Sorry, Yifei?
Yes?
Yeah, you say it depends only on Q and lambda I, so you mean it doesn't depend on what?
It doesn't depending on which state it is. I mean, the key point is that it depends only on the which affine temporally module. So if you have many eigenvalues that belongs to the same affine temporally module, then the ratio of the amplitudes of all these states are the same. Is that clear?
Yeah, thank you.
Okay.
But why is this amazing? Isn't this just a consequence of temporal loop symmetry?
I mean, I don't think one knows how to calculate this amplitude using the symmetry itself. We know that the spectrum comes as representation of the symmetry, but I don't think it says anything about this amplitude. So, and also these amplitude ratios do not depend on the lattice size. And from the lattice, we managed to extract of many of these amplitude ratios, which in general are given by rational functions of Q, which I'm giving some examples like this. So as we said before, in the continuum limit, these eigenvalues give us the scaling dimensions of the operators which appear in the spectrum of the connectivities. And so the fact that these amplitude ratios depend only on the affine temporally modules tells us that in the CFT, different operators which belong to the same affine temporally module has a rigid relation. And what does this mean more precisely? We can consider connectivity, let's say PAAA, and we said that in the CFT, we're going to expand it using the conformal block expansion with the spectrum of these operators belonging to this the operators belonging to this spectrum, each one with a certain amplitude. But of course, we can rewrite this sum in the following way, that we sum over all the affine temporally modules that appear in the spectrum, each one with some overall amplitude. And then we write a sum of all the conformal operators belonging to this module with some relative amplitude times its conformal block.
Are you going to explain how the temporally leap algebra acts on the CFT states?
I mean, I don't know how precisely, but I'm going to talk about how to construct their relation. And
but you already said there is a module of, you said already that the CFT states form a module of W, but it means that you have some algebra, you know how to act on the CFT states. Otherwise, how can you speak about the module?
Well, that's on the lattice side. And
no, but here it's already CFT side.
Yeah, but
I mean, you said module.
Yeah, it's the module of this lattice algebra.
Okay, then you know how algebra acts on the CFT states.
Well, I don't know how it does that.
Well, but, then you shouldn't say module because you are confusing.
But why can't you talk about the module of?
Well, module in mathematics means that there is an algebra. It acts on the vector space.
Yeah, on the lattice.
Yeah, but here you're talking about CFT already. You said HH bar belongs to W. So what does this exactly mean mathematically? Because
these eigenvalues of the transfer matrix give us the scaling dimensions of the operators. And this is more like an observation from the lattice side to deduce some relations on the CFT.
But it's not yet a module. Module means that you have an algebra, it acts on the vector space. You have a vector space of states. For example, if Virasoro acts on the vector space of states, it's a module. If you have a bigger algebra, you have rules how it acts on this vector space, then you have a module. If you don't have the rules how it acts, you should not call it a module. You should call it something else.
Okay, so then...
Well, it is a module, Slava, but it's on the lattice. You have a finite vector space, which is a Hilbert space. You know, it's 2 to the L, for instance, for Ising on L sites. And temporary leap acts on this. And then you have representation and temporary leap. And it's just that we know the dictionary between representation and temporary leap and what that becomes as a state in the continuum. So there's a dictionary in this way. But temporary leap acts on the lattice, not in the CFT.
But do you know how a temporary leap acts on the CFT state? I give you like
it doesn't act on the CFT, it acts on the lattice. There is no temporary leap in the CFT.
Then you should not say it's a module, you should say something else.
It's a module on the lattice. There's a vector space of the finite vector space on which the transfer matrix act. And you can perfectly talk about module. But it's not module in the CFT of the space.
Well, yeah, I'm confused.
It's all lattice stuff.
If you know how it acts on the lattice, if you know some algebra and how it acts on the lattice, if you know which lattice state corresponds to which CFT state, why can't
but the lattice Hilbert space is much bigger. It includes high energy states that have no description in the CFT. It's only the low energy part on the you have to do a scaling limit, and only the low energy part of the lattice vector space will map to some CFT state. There's a whole part of it that doesn't map to anything.
Okay, have you seen Benoit discussion on Slack? There was Azat Jasper were contributing to the discussion. Have you seen Yefei the discussion on Slack?
Yes. I mean,
so Azat claimed that he knows how to act with this temporary algebra on the CFT states. Now Jesper said also that he knows. Now you say that it does not. So,
I don't know how, but yeah.
Okay. Also for me, I don't know that it acts, but okay, maybe it does, but it doesn't have to. Put it this way. You can talk about module already on the lattice.
Maybe we can talk about this more in more detail later.
But that's a key point actually, because because it draws a line between because it draws a line between what we know and what we don't know. So anyway, we can try to come back to this, but I don't understand what it means. HH bar belongs to W. I know the spectrum of this theory. So
HH bar are the scaling limit of some state on the lattice, and these states on the lattice belong to this module.
HH bar are states on the lattice. No, HH bar are not states on the lattice. HH bar are
states they're the conformal dimension of the operator, which comes from the scaling limit of these states on the lattice.
Well, if you don't, I don't understand this equation. This seems to me a very important equation. I don't understand what it's meant by this. So
but
now you can
is it clear that when I say that, I mean, that they obtain the spectrum on the lattice, that in the CFT, they give rise to some conformal operators that you accept?
No, everything up to this point was clear. That was the first non-clear equation.
Okay, so, I mean, I don't know what's so confusing, but each conformal operator comes from a lattice origin, which is organized by the fine temporal representation. And so you can also talk about these operators in the CFT that are organized by these lattice algebra. Is that so weird?
What is weird is that why don't you, so if there is indeed this one-to-one, you seem to suggest that there is one-to-one correspondence between lattice objects and CFT objects.
Well, I don't know what you mean by objects, but
by object, by eigenstates. Is there one-to-one correspondence? Like, is there between CFT states and lattice states?
It's not a one-to-one map, it's a scaling limit. If you're on the lattice, you have finitely many states. Now, for instance, take the highest way state of such irreducible W representation. This in the scaling limit will become, for instance, a primary state in Virasoro. So state by state on the lattice, you have to send the system size to infinity, and you can map a lattice state, actually a sequence of lattice states, to a state in the continuum.
Okay. Okay, then if you take two lattice states, I can understand that you say, Benoit, that the temporal leap acts on the lattice side. So I know how this lattice states indeed form a module under temporal leap. So let's take, for example, a particular element of temporal leap, act on some lattice state. It will give me another lattice state, so it's a module.
On the lattice,
so now let's take two CFT states and let's take a very fine lattice. So I will find very good lattice states which are almost equivalent to the CFT states.
Mm-hmm.
Why can't I, from this information, say that my temporally loop algebra is going to act on CFT states?
You know, what could happen is when you act on the lattice with a temporally leap generator on a state that has a well-defined scaling limit, it will also produce lattice states that do not have a well-defined scaling limit because they have super high energy. When you act on a lattice state with a temporally leap, you have a linear combination of all kinds of lattice states. Nothing tells you all these states would have a well-defined scaling limit.
But the two states, I mean, let's just look at the second line. I'm sorry, Yifei, I'm interrupting you, but this is a crucial thing. I mean, if you don't understand this, then I can basically just decouple and go do something else.
Okay.
So I would like to understand this point. So let's just look at the second sum, and let's look at two terms in that sum, which you somehow, I would like to understand by which principle you put them in this sum. So two states with different HH bar, which you would like to put in the same temporally leap module in the second line of this formula. Can you describe me just the algorithm? How do you put two things with different HH bars in the same, you know, how do I define which are belong to the same module and which not? Because given all these caveats that Benoit just said, that, you know, you act with temporary leap, you can get states which don't have a well-defined continuum limit. So given all these caveats, what is the algorithm?
I mean, I'm not, I don't know a lot about lattice, but my understanding is just that each of these eigenvalues of the transfer matrix gives you some operator with a certain conformal dimension in the scaling limit. And we do this just by looking at the these eigenvalues, which module it belongs to, then we say that these conformal operators belongs to that.
I mean, for me, it would be enough to just give one example. Can you give 2 examples for 2 different values h and bar for 2 different CFT states, which,
yes, so,
according to you, belong to the same module?
Okay.
And you explain why, and you explain
maybe,
what is the reason why they belong to the same module. How do you arrive to this conclusion? I think that would completely clarify the situation.
Maybe because I did not give any concrete example of what these modules are, but in general, so suppose we parameterize the conformal dimensions using the H of RS, then each of the, I mean, these are non-chiral fields, but each of this module includes the conformal fields with R shifted by 1 indices from 0 to infinity.
Can you explain why? I mean, just take 2 states which you just claim belong to the same module and explain how you arrive to this conclusion from the lattice.
I mean, the thing is that I did not put anything in the slides, but maybe I can use this fancy function of annotating. But how do I do that? Okay, so, but then I cannot.
You can write on it.
Yeah, I'm going to some slides that's appropriate for this. So, so suppose we have some module that's on the lattice. I'm gonna label it as J1. It doesn't mean much at this point, but it will include the conformal operators with dimensions, with the CAC indices J0, J1, J2, and so on. And on the lattice, these J indicates some kind of geometrical properties of in these loop representations of how many lines go through the cylinder. And then the other indices comes from looking at its spin on the cylinder, which you can think of as the conformal spin. I mean, it's not very clear, but I don't understand what precisely you want.
Well, can you give me an example of 2 states on the CFT, just 2 states which belong, CFT states, which belong to the same module?
Okay, so let's say one is the identity operator. And then the next one is 1, 2. These are diagonal fields, 1, 3, and so on. These belong to the same affine temporal leap module.
Okay, can you now explain how you arrived to this conclusion?
Well, I did not arrive this conclusion. It's
you did not, but you know how it's arrived at, and can you explain how one arrives at this conclusion? Through which steps one has to go through, what kind of calculation on the lattice one has to do in order to see this?
You know the spectrum of the transfer matrix because it's integrable. So in the CFT, you can just read off the conformal dimension of everything. That's it. So you know what CFT state is in which irrep.
But don't you see that this is in contradiction with the caveats that you mentioned? Because if everything were as simple as you say, why can't you figure out how temporally labeled algebra acts on the CFT states?
Because you can only map the low-lying part of the module of the temporary leap is huge. Only the low energy part of it will map to a CFT state.
Okay, then there is some part of temporally lieb algebra which will act on the CFT states and some other part which is going to give you junk. So you can still extract some part which will act properly.
But you could imagine that you act on the low energy state with a temporary leap and it just produces a linear combination of everything in the module.
No, but look, these two states, 1, 1 and 1, 2 on the lattice, they sit in the same module. So there is some temporary leap generator which maps 1, 1 to 1, 2.
Not one temporary leap generator. All you can say is a temporary leap generator acting on
some
1,
element
1
of the algebra
X. It will produce some linear combination of everything, including 1, 1, 1, 2, and some other chunk.
You can actually make a sort of discrete version of the Virasoro generators, and it will be a particular combination of the temporary leap generators. So I guess that's maybe
for example.
Yes, you can do this. So this was done already in the early 90s. It's called Connectivities generators.
Yeah, that I know actually. That's a nice example. Yeah, that I am comfortable.
So this way, yeah, you can start with one state and you just map it to the other. Yeah.
Okay, but now you say that there are more generators. Because
the states that will actually correspond to something in the CFT, they're called scaling states. They differ from the ground state in a very particular way. So you're only allowed to map these to something in the CFT. And yeah, in general, you could act with just any temporary leap generator on one of these, and you get something that's not a scaling state.
No, but is there some temporary leap? Is there some fancy combination of temporary leap generators? Which similarly to how Kasteleyn
I mean, that's a fancy
scaling states to approximate scaling states to approximate scaling states, which map approximate 1, 1 to approximate 1, 2.
Sure. Yeah, I mean, that the Kasteleyn generators are a particular combination of temporary leap generators. That's what they are.
No, but now we are saying there's more. Because if you just include Kasteleyn generators, you will only get Virasoro in the scaling limit, and you will not get 1, 1 and 1, 2 in the same module. There are some extra generators which map 1, 1 to 1, 2, some extension of Kasteleyn.
Sorry, I don't see what you're looking for.
I think what he was asking is what's the CFT generator that gives rise to this affine temporary leap module instead of the usual. I'm not sure. That's my interpretation.
Yeah, in the continuum limit, there have to be some extra. Just like Kasteleyn generators mapped to Virasoro in the continuum limit, there have to be some special combinations of temporary algebra which map to something in the continued limit that maps 1, 1 to 1, 2. Is there such a thing or not?
I don't think that this is well understood. That the precise continuum limit of this algebra.
Okay, well, that's, I'm confused because Azad said that he completely understands this, and then Jasper also said that he was saying the same thing. Now he's silent.
But, I mean, my interpretation on this is completely from the CFT perspective, but
I think he's not there.
Okay, maybe.
But that is there. He can answer.
Okay. Anyway, Ife, sorry for this big interruption, but I'm more comfortable. So, yeah, I'll try to be more.
The short reply, Slava, to you that I mean the picture I think is not. I'm not sure if 1, 2 and 1, 3 are the primary fields, or they are descendants of 1, 1.
No, it's the primary fields.
They're primary fields. Okay. Because in my picture, so there are extra generators. You can cook up out of temporary leap generators some combinations which are like Kasteleyn, and on the low-lying part of the spectrum, they mix different primary fields for the Virasoro. You can construct them, and you can analyze it explicitly in some examples, like pre-fermionic examples. But in general, Q-state models, Q-state Potts model, I don't know. But they sit inside these extra generators, which I call interchiral generators. They sit inside affine temporary leap in the sense that you can make like a Kasteleyn form expressions, so that they give you an irreducible representation in the scaling limit out of irreducible representation of affine temporary leap. So if you start with affine temporary leap representation which is irreducible. On the low-lying part of the spectrum, the temper leap, of course, just gives you all the necessary operators, so it stays irreducible. In particular, there should be generators that mix different primaries. And in some particular examples, we can explicitly construct these combinations of temper leap generators that mix them.
So just to summarize, some people say that there should be some extra generators which map these primaries one to the other, but in this particular example, it has not been worked out.
In this particular example, it was not worked out. I have simpler examples, like based on some free fermionic systems, or basically, in this picture, it would be something like limit Q to 0, like dense polymers.
Okay.
In that case, it can be worked out very explicitly and rigorously. These operators that mix the states, they were constructed.
Okay.
So this you can analyze very explicitly and mathematically rigorously, and construct them. Actually, the mathematical construction behind it is inductive limits. So you can say properly mathematically what does it mean in which sense temper leap generators act on scaling states, but in inductive limits. So the mixing operators can be constructed, but in this general Q-state Potts model, morally they are there, but I don't think it was worked out explicitly.
Okay. Thanks.
But sorry, it's not that you take the transfer matrix, diagonalize it, it is block diagonal in each of these modules, and then you look at which eigenvalue you get according to a certain lattice realization of L0. Isn't it some numerical observation based on diagonalizing the transfer matrix? What you are saying, there's not any mathematical proof of it.
No, it's all integrable. You can just compute the spectrum analytically.
Maybe we could resume the talk.
Well, some people are confused. For example, Jakub would just ask a question. So it's
yeah, well, maybe this can be postponed to Slack or to the discussion after the talk.
okay.
Okay, so I continue. So, okay, so, I mean, let's say that we rewrite it this way. And this lattice observation of these amplitude ratios, what it tells us, right? So what it tells us is that, in fact, the ratio here are some universal quantities that does not depend on which connectivity that we're talking about. And so what we're going to do is to call this object here an interchiral conformal block that's associated with the entire affine tempered leap module. And the key point is that it's the same interchiral conformal blocks that enters the different cluster connectivities and also these pseudo probabilities which appears in the cluster formulation of the minimum model 4-point functions. So yeah, so this name of the interchiral comes from this earlier work where they studied on the lattice and postulated an interchiral algebra, which is larger than the Virasoro times the Virasoro bar. And there it was generated by fusing with the energy operator, which we're also going to see, which will play a role in constructing these interchiral conformal blocks. So what we are going to do is to write these cluster connectivities as an expansion using these interchiral conformal blocks, and each one with, for each affine tempered leap module, there's an overall amplitude, and then bootstrap these amplitudes. So at this point, I want to point out some interesting observation that we can in fact extract some of the pulse amplitude that appears in the connectivities from the analytically known minimal model amplitudes. So let me just erase these things. So to do this, we consider this combination of the correlation function, of the geometrical type, and we said that we are going to expand them using these interchiral blocks, each one with a certain amplitude, and so it can be written in this way. And on the other hand, we have identified this certain combination of the geometrical correlations to be to reduce to the minimal model 4-point function. And in that case, the amplitude that appears there are actually analytically known. I'm going to refer to it as the Liouville amplitude, which is closely related to the C less than 1 Liouville theory. But in this case, it corresponds to the non-diagonal generalization. So by comparing the left-hand side and the right-hand side, we see that we have this relation of these amplitude appearing in the connectivities and the pseudo probabilities related to the analytically known Liouville amplitudes. And then the left-hand side can be further written in terms of these amplitude ratios, which for the moment, we know some of them from numerical lattice extraction, but perhaps one day one can figure out how to derive these amplitude ratios from a first principle. But the point is that from this equality, so if we have some fields which appear both in these 4-point function of the minimal model 4-point function, and also in the spectrum of the connectivities, then using these ratios, we can actually write the amplitude appearing in pods in terms of these analytically known Liouville amplitudes. But on the other, so we managed to write some of such expressions which are given in this way. And on the other hand, we also know that in the minimal model 4-point functions, there's a very sparse spectrum. And so some of them some of these fine temporal leap modules under this combination does not survive in this 4-point function. In this case, we will have the Liouville amplitude vanish, but on the other hand, the amplitude in the connectivity does not, which means what's in the parentheses vanish, which provides another consistency check of these lattice observed amplitude ratios, which turn out to be true. So to construct these interchiral blocks, we're going to use the fact that the energy operator, which has the indices 2, 1, is in fact degenerate. And it's known that this kind of degeneracy can lead to recursions in the OP coefficients. And this kind of technique was used to solve the Liouville theory in these classical papers. And it was also recently generalized to the non-diagonal case in this work. So what I'm going to talk about now is I will review the basic elements of this technique and then see how to use it in the case of the pods connectivities. So the key point here is that since we have some degenerate field, then a 4-point function involving such degenerate operator actually satisfy the BPZ equation. And when we fuse it with another operator, it truncates into 2 terms. The fusion will truncate into 2 terms. And in terms of the conformal block expansion of the 4-point function of such type, it also truncates to 2 terms where the dual S-channel blocks and T-channel blocks are known solutions from the BPZ equation. There's a linear relation relating these, which also provides the linear relation of the amplitudes appearing in such expansion. And by playing with several correlation functions of such type, one can obtain a recursion of some arbitrary amplitude as long as the R index is related by shifting 2 units. in the case of Liouville, one also assume another degenerate field given by the indices 1, 2, and this leads to another set of recursion of the amplitude. And in that case, combining the two give a full analytic solution of these amplitudes. But in this, the second degeneracy does not exist in the case of pots. So in the case of pots, to construct these interchiral blocks, we need something more stronger since the conformal fields that belong to the same module are related by shifting the R index with 1 unit. So we want to find the amplitude recursion of this type. And in terms of the OP coefficients, what we want is some OP coefficient square, this ratios of 2 spin operators fusing with the field RS and R+1S. So the key to obtain such a recursion is by looking at the crossing equation, which involve the energy operator, and it has an energy operator, 2 spin operators, and some arbitrary field RS. Then by looking at the S channel, by fusing the energy with the spin, we get another spin operator in the intermediate channel. And at this vertex here, we get the OP coefficients of fusing 2 spins with the field RS. For the T channel, by fusing the energy operator with the field RS, we get an R+1S in the intermediate channel with, at this vertex, we get the OP coefficient of fusing 2 spins with the field R+1S. So from this equation, we get the ratio that we want times some other stuff, which is equal to some known stuff from this, the BPZ equation. And these other stuff can be obtained explicitly by studying 2 more 4-point functions of such type. So we get the recursion of the amplitude that we want to relate different fields in the same module. And then the
Sorry, if may I ask a question? Why is there a single fusion channel?
Sorry, there are 2 fusion channels, but we look at one of them. So so in here you get 3/2 and 0, and but then you have a spin here, right? And the other one you get R-1, R+1. But what we're interested in is this channel, particularly for the corresponding OP coefficients.
But why would there be equal? If you change channel, one should be a linear combination of all possible channels. No?
I mean, this equation is a crossing equation. So from this equation, we get that this vertex times this vertex is related to this vertex times this vertex and by some known function. And these are this other stuff that I'm saying here. And I'm not giving the detail of, the known stuff that I'm saying here. And then this vertex with this vertex are the other stuff which you can obtain by looking at 2 other 4-point functions of this type. So from this, we can get the ratio. So,
but I don't understand. So you're looking at just one conformal block on the left in a certain channel.
So in this case, there are 2 channels, right?
All right, but this symbolically just means one of them, or?
This means that, I mean, I'm looking at one of them. So the 2 channels are given by 2 degenerate conformal blocks. And I'm relating the one of them with one of them in the S channel with the one of them in the T channel.
That's what I don't understand. Typically, one of them in the S channel would be a linear combination of the 2 possible ones in the other channel. I mean, the change of basis is a 2 by 2. I mean, it's not one conformal blocks equals one other. It's a linear combination of.
But you also know that the 2 channels in the S or T are related to each other in this way that you obtain the recursion for the Liouville, right? So you can express the other channel using the channel that you're interested in. So in the work that, I mean, you did and Sylvain did, what one look at is the two channels in the S channel conformal block expansion or the T channel conformal block expansion, which are related by these, but you know that already. And now the other channel you can express, the other channel in the T channel, you can express it using that relation that you already know.
All right, maybe keep going, but that might become clear later. It's maybe just a picture you draw that's just disturbing. So just
okay, I'm just trying to, I'm being sketchy here, but yeah, okay.
It's fine. It's okay, thank you.
So, so then what we are going to do is to expand these connectivities using these interchiral blocks in the S channel and T channel, and each one with a certain spectrum, and these spectrum are for different connectivities are related by crossing, and each one we have a certain amplitude that we want to bootstrap, then put it into the numerical program we solve for these amplitudes. So the results are given in these plots. What I'm plotting here are these overall amplitudes as a function from of Q from 0 to 4, and the different colors indicate the different connectivities that we're interested in. And from these plots, you can see that there's some singularities in this amplitude that I'm going to explain in more detail later. But the first thing that we want to compare is these amplitude with the lattice computation. And so that's what I'm plotting here, where the crosses are the lattice results, and the red and the blue dots are the bootstrap results. We can see that they agree to a very good extent in terms of order of magnitudes and the analytic structure as a function of Q. But there is some small discrepancy, which is mainly due to the finite size correction for the lattice computation. In general, the lattice are less precise compared to the bootstrap, but it gives us some confidence that we're indeed bootstrapping the correct physical quantities. So what I want to explain now is how to understand some of these singularities that we see in the amplitude. I'm going to take the example of this module, which includes the following primary fields with their descendants. And this module appears in the spectrum of both the connectivity AABB and the connectivity AAA. If you look at their amplitudes in these two different connectivities, we see that for the former, there's a pole at the percolation point, Q equals to 1. This is also reflected on this lattice numerical observation of these amplitude ratios. And so one can look at the spectrum of these two different connectivities, and we see that for the former, it has an actual module, which in particular includes the identity operator in it. So what I'm going to explain now is to how to understand this difference in the analytic structure of the amplitude and the difference in the spectrum of the connectivities, but purely from the Virasoro conformal symmetry point of view. So
that's the question.
Yeah.
So these poles, I originally, like before your talk, I thought that these poles really, like, they should be unphysical and they should never be there, and then this is part of the motivation to look for ways to remove them. But now you explain that this amplitude with poles actually has this physical interpretation in terms of the RSOS version of the loop model with pseudo probabilities. So it means that in some loop models, there can actually be poles. This I find really puzzling. Can you comment on this? So why is it that in this RSOS model, there are poles as a function of Q?
So the correlation, the 4-point function in this RSOS model I mean, in the type D, I don't think it's well defined for the whole range of central charge between -2 and 1. So if you naively analytically continue the type D minimum model to a generic central charge, you will find some singularities of this type. And it's precisely that in the case of pods, we don't have such singularities. And this is made sure by this complicated spectrum that we're dealing with. And I'm going to talk now how to understand this spectrum, how it cancels the singularities. Yeah. So at the Q equals to 1, the conformal dimension of the identity operator collide with the conformal dimension of this field labeled by 1, 2, which falls into the CAC table. And this means that if we look at its conformal block, it includes this term, which has a pole at Q equals to 1, and the remaining term as a function of Z, which is a conformal cross ratio, takes the form of the conformal block for the field H12. And similarly, we have the antichiral part. And so combining the left and right, we see that the non-chiral conformal blocks for the identity operator has the following term, which has a singularity at Q equals to 1, and its coefficients has the behavior of the conformal block for the field H12, which belongs to this module. And in general, we don't expect that these connectivity quantities, we expect these connectivity quantities to be a smooth function in Q and does not have any singularity as a function of Q. And the only way to cancel this kind of singularity at Q equals to 1 is such that the amplitude of this module has also a pole at Q equals to 1 with the opposite residue. And this residue is completely determined by the Virasoro conformal symmetry. And so by contrast, when we look at this module in the connectivity AAAA, we don't expect such pole because as we see before in the spectrum of that connectivity, we don't have an identity operator there. So it doesn't cause this kind of pole that one needs to cancel. So from this, we see that we expect the ratio of these amplitudes of this module in these two different connectivities to have this kind of analytic structure, which give us some idea about how to understand these lattice extracted amplitude ratio from just a CFT point of view. And then we also see that we can in fact extract the amplitude in AAAA as a residue of the amplitude in AABB, which from the residue of this expression, which is completely determined by the Virasoro symmetry. So the expression of this is given by this, which one can just play with the conformal blocks and see this. And then I'm here plotting this exact amplitude in its analytic form at Q equals to 1 together with the bootstrap result, which we see that it interpolates smoothly in these bootstrap results. And when one can actually play this game for these bootstrapped amplitude in general, and in each case we understand how to interpret these singularities, and it usually allows to extract some exact amplitude at a certain special point of Q, and also we get some intuition about this interplay between the difference of the spectrum in the connectivities and the difference in the analytic structure in Q. So the last thing that I want to say is we said before that in the non-diagonal generalization of the C less than 1 Liouville theory, one actually has another field, which is given by 1, 2, which is degenerate. And this leads to another set of recursion in the amplitude, which in the language of the fine temporally, relates the amplitude for different modules. And in that case, from the degeneracy of H21, which we just talked about, the two sets leads to a full analytic solution of these amplitudes. But in the case of pods, we have the second degeneracy here, which is the energy operator degeneracy, but not the first one. So we don't expect that in the pods, these kind of Liouville recursions to hold. But we observed that in the case of pods, there's actually a renormalized version of these Liouville recursion, which means that when we look at the amplitude ratio that relates these different modules, they are given by the usual Liouville recursion that as a result of this degeneracy here, with in addition some extra factor that is given by rational functions in Q, which for the moment, as far as I know, there's no derivation of how to get these rational functions. But it's an interesting fact that there's such an expression that exists, which would suggest that there might be some analytic solution of these expressions, which would be a very interesting aspect to look into. So to briefly conclude, from these investigations, I think maybe it's optimistic, but we may not be very far from more analytic understanding of the pulse connectivities. And to make progress in this direction, one has to understand better the symmetry aspects, and also for these renormalized Liouville recursion, what replaces the usual Liouville recursion in the case of the usual Liouville degeneracy in the case of the pods. And some other important topic that was not covered in this talk is the recent progress in understanding the logarithmic CFT aspect of the 2D loop models. This was first understood in the case of ON by Gorbanko and Bernardo Zan. And then in this paper of Nives Vivat and Ribot, they also constructed the logarithmic representation of the Virasoro algebra, which appears in the case of pods. And in another, and then also they have tested this to a high precision using the bootstrap. And then in another paper, we have also investigated this logarithmic modules in the CFT and find some lattice evidence for their existence. So now the picture about this logarithmic CFT at generic central charge is for the loop models is relatively clear. And some further direction to investigate is to look at the C equals to 0 logarithmic CFT. This is some work that we're working on. So I will stop here. Thank you.
Thank you, Yifei. Are there questions?
Can I?
Yes.
Hi. So, coming back to the initial question of Ilya, actually, so you are, this is, we are describing the cluster, right? So, typically one can think that in the same, there is a sort of homogeneous CFT setup. We describe the cluster and the very boundary, right? And in another approach, which is called conformal loop ensemble, typically what you typically study are this the perimeter of this cluster. So one thing is that, for example, the conformal dimension of these loops are related, to, for example, to the fields, I think 0, 1, field 0, 1 in your notation. Okay, so
you mean the two-leg operator is what you're talking about?
Yes, I mean, like the like if you compute, like for example, you start by looking at the probability that 2 points belongs to the same perimeter. Right?
Okay.
And this is like one field which is, I don't know, like I think it is 0, 1, not 0, 2, 0, 1.
Okay.
So it does not enter in the spectrum, but so one thing is that if you ask, like for example, one probability we don't know to compute, I mean, at least I didn't know to compute, is like the probability that 3 points belongs to the same loop.
Mm-hmm.
Okay, and this is not given by the, it seems, by the Liouville structure constant. I think it is even singular, this. So my question is, I mean, do you start to because in your bootstrap solution you see other structure constants which are not given by Liouville, and that also contains this, for example, this sector of fields are like 0, 1, or 0, 2, and so on. Do you have this? I mean, do you think that this bootstrap equation can describe? So the general question is: do you think that this bootstrap equation can describe also like the boundary of this cluster? Yeah.
So you're talking about you're talking about 3-point functions, right?
I'm talking about instead of like you can instead of looking the interior of the the cluster, you look at their exterior, their contour, and still you have a bunch of like you can like observable, like the probability that 3 points belongs to the same contour, for example.
Okay.
So this structure constant is not Liouville, but maybe in one can access to these values like using in the same theory, in the sense that, for example, in your bootstrap approach, finally you find like an amplitude that actually can describe this observable. Or maybe not, because there are some examples in which the interior of a cluster has a different CFT from the boundaries. I mean,
yeah, so I mean, I guess what you're saying is closely related to the correlation functions in the Owen loop model, right? But maybe you're talking about the dense model instead of the dilute one. I mean, in the Owen model, I think one can also do this kind of bootstrap approach to consider like different configurations of 4 points, but in this case, the loops goes through the operator instead of the operator are inside.
yes.
Yeah, so I think that's something that people at Saclay are working on. But I think the idea is very similar. And I imagine one can also write some kind of interchiral blocks of that type, but that's going to result from a different degeneracy, which is because the energy operator in the Owen model is different from the case of Potts. But I think the approach would be similar. I don't know whether anyone wants to comment on that because I'm not working on this myself.
Yeah, someone working on conformal loop ensemble or typically is interested in this. I mean, but. So thanks.
Thank you.
Are there other questions?
I have a naive question, sorry. At the end, do you know how to plot these functions?
Yes. I mean, numerically.
I mean, what do you know exactly and what remains to be calculated? This is the question.
I guess we don't know the full analytic expression of these functions, although the numerical result tells us about what they look like a lot, but we know some relations that's from the numerical observation, but we don't know how to derive them, things like this.
But basically, numerically, with the bootstrap, you can fix all of the amplitudes. It's A's.
Yes.
This you can do it.
Yes.
What you don't know if there is an analytic expression for the A's.
Yes.
Okay, thank you.
Yeah. Other questions? Well, if not, let's...
Maybe one quick question. So in all this bootstrap, I guess you... do you have to assume that the CFT is not logarithmic technically, or?
No, I mean, the way we do it at that time, we did not know how to deal with this logarithmic conformal blocks. So numerically, we made some approximation. So the amplitude that results from this in the work that I'm presenting here would not be like arbitrary precision results, although it tells us a lot about these amplitudes. And I think with the logarithmic consideration, then Sylvain and collaborator have constructed these logarithmic conformal blocks, and then one can then put those into the bootstrap to study the amplitudes, which would go to a higher precision.
Okay, thank you.
Okay. So if there are no more questions, let's thank Yifei again.
Thank you.
And, that's all for today.
Okay, thanks.